Space has a flaw, a hard stop, a place where the laws of physics shatter completely. Zoom in past atoms, past the smallest particles ever detected, and you hit a wall so deep that measuring it creates a black hole. The universe literally fights back. We'll explore what happens when gravity and quantum physics collide, why time loses its direction at the smallest possible scale, and how a single particle of light at this depth would weigh as much as a flea. If you enjoy what we do, a like and subscribe keeps us going. Now brace yourself. We begin. Take a piece of paper, tear it in half. Now tear that half in half again. Your brain tells you this can go on forever. Keep cutting, keep shrinking, keep dividing, and eventually you reach something so small it defies imagination. That instinct feels logical. It feels like basic math. Half of something always exists. There is always a smaller half waiting on the other side of the cut. Physics says otherwise. The universe has a flaw, a hard boundary where the act of dividing space stops producing smaller space and starts producing something else entirely. Chaos, destruction, and a complete breakdown of every rule we use to understand reality. This boundary is called the Planck length, and reaching it does not reveal a smaller world. It reveals the end of the world as physics can describe it. Here is what makes this strange. The Planck length is not small in the way a grain of sand is small, or even in the way an atom is small. It sits so far below everything we can detect that our best instruments cannot get within a billion times of touching it. An atom already feels impossibly tiny. A single human hair is roughly 1 million atoms wide. Go smaller, and you find electrons orbiting at distances that make the atom feel like a stadium. Go smaller still, and you find quarks, the building blocks inside protons and neutrons. Then keep going. Past quarks, past every particle we have ever measured, past every scale where our tools mean anything at all. The Planck length waits at the bottom of all of that. And at that depth, space itself stops behaving like space. Most people imagine space as a perfectly smooth fabric. Zoom in far enough and you expect to see the same smooth, quiet emptiness, just at a smaller scale. Every instinct we have, every map we draw, every coordinate system we build, assumes that space keeps its shape no matter how deep you look. The Planck length is where that assumption collapses. Below this scale, the geometry of space dissolves. There is no here, there is no there. Distance stops being a meaningful concept. To put the size in perspective, if you took a single atom and expanded it until it was as wide as the entire observable universe, the Planck length inside that expanded atom would still only be the size of a regular tree. That is the kind of scale we are dealing with. A distance so vanishingly small that our language barely handles it, and our math only handles it by breaking. Every measurement humans have ever made, every ruler, every laser, every particle collider exists far above this flaw. We have never touched it. We have never come close. And the deeper you think about why, the stranger the answer gets. Because the Planck length is not just the smallest thing we happen to be unable to measure right now, waiting for better technology. It is the smallest thing that can exist inside a universe governed by the laws we live under. Push past it, and you do not find something smaller. You find a contradiction, a place where two of the most successful theories in all of science turn on each other and destroy the measurement before it can happen. Something built that wall, something enforces it. And the man who first noticed it was not looking for a wall at all. He was just trying to clean up some messy equations in 1899. What he found instead changed everything. Max Planck was not trying to rewrite physics, he was trying to fix a minor embarrassment. In 1899, scientists had a problem with something called blackbody radiation. When you heat an object, it glows. Heat it more and the colour shifts. A fire poker goes from black to red to orange to white as the temperature climbs. Physicists had equations to predict this behaviour, but those equations broke down at high frequencies. They predicted that a hot object should release infinite energy as ultraviolet light, which was obviously wrong. Objects did not explode with infinite brightness. The math was simply bad. Planck was a methodical man. Careful, precise, the kind of scientist who found comfort in numbers lining up cleanly. He began adjusting the equations, searching for a fix, and he found one. But to make the math work, he had to introduce something radical. He had to assume that energy came in discrete chunks, like coins, rather than flowing in a smooth and continuous stream. He called these chunks quanta. He hated this idea. It felt unnatural to him, almost like a trick. He spent years afterward trying to make the quanta disappear back into classical physics. They refused to disappear. And the mathematics he built to fix his blackbody equations contained something he had not noticed immediately, hiding inside the constants he used to make it all work. Planck had used 3 universal constants in his equations: the speed of light, which governs how fast anything can travel, a gravitational constant, which governs how strongly mass curves space, and his own new constant, now called Planck's constant, which governs how energy behaves at the quantum scale. 3 separate measurements, each discovered through entirely different branches of science, each describing a completely different piece of reality. He noticed that you could combine these 3 constants in a specific way and produce a unit of length, a distance baked into the fabric of physics itself, using only numbers the universe provides. No human choices involved, no arbitrary units like inches or meters or miles, which humans invented and could have invented differently on another day. This length came entirely from nature. That length was the Planck length. And something about it was immediately unsettling. Other units humans use depend on human choices. A mile is a mile because people decided it was. An inch exists because someone measured it once and wrote it down. But the Planck length would be calculated identically by any civilization anywhere in the universe, using the same constants, getting the same answer. It belongs to reality itself. Planck mentioned this in a paper and moved on. He had no idea what it meant physically. He thought it was mathematically elegant, but perhaps not meaningful in the real world. He could not have guessed that 60 years later, physicists would return to his number and discover it marked something terrifying, the exact scale where the 2 greatest theories in science stopped working. For now, the number just sat there in the equations. Patient, waiting, the next question was obvious. If this scale exists, can we ever reach it? Can we measure it? And the answer to that question starts with understanding how measurement itself actually works at extreme scales. The answer is stranger than almost anyone expected. Imagine trying to feel a single grain of sand hiding under a heavy blanket. Your hand is too big, the grain is too small. You press the blanket with your fingers and feel nothing useful. Now imagine using a thin needle instead. The needle is closer in size to the grain, so it picks up the bump. The tool has to match the scale of the thing you want to find. This principle works the same way in physics, but the tool is light. Scientists do not touch subatomic particles with physical instruments. Instead, they fire beams of particles or pulses of light at targets and watch how those beams bounce back. The pattern of the bounce tells them something about the shape and size of the target. It is the same basic idea as using sonar to map the ocean floor. Send a signal out, measure what comes back, and reconstruct a picture from the data. The critical rule is this: the wavelength of the probe has to be smaller than the thing you are trying to see. Wavelength means the physical length of one full wave cycle, the distance between two peaks. If that distance is larger than your target, the wave washes over it without registering anything. The target becomes invisible to the probe, the way ocean waves roll past a tiny pebble on the seafloor without changing shape. Visible light has wavelengths that are far too large to see individual atoms. Atoms are roughly 10 billion times smaller than a centimetre, and visible light waves are hundreds of thousands of times larger than atoms. Using visible light to see an atom is like trying to use a fire hose to examine a single grain of sand. So scientists use different kinds of waves. X-rays have shorter wavelengths, which is why they can pass through skin and reveal bones beneath. Electron microscopes use beams of electrons, which behave like waves at the quantum scale, with wavelengths small enough to image individual molecules. The principle scales up: shorter wavelength, smaller detail visible, more information extracted. To see something at the scale of a proton, you need a wavelength roughly the size of a proton. Particle accelerators do exactly this. They slam particles together at enormous speeds, using the debris from collisions to reconstruct what exists at small scales. The faster the particle travels, the shorter its effective wavelength, and the finer the detail it can reveal. Here is where the problem begins to show its teeth. Shorter wavelengths require more energy. This is a fixed law of physics. To cut your wavelength in half, you have to double the energy of your probe. Every time you want to see something 10 times smaller, the energy required climbs enormously. To see a proton clearly, modern accelerators use energies that took massive engineering to achieve. The accelerator at the European Centre for Nuclear Research stretches 17 miles in circumference just to reach proton scale. Now imagine the scale you need to reach the Planck length. The Planck length is roughly 100 million billion times smaller than a proton. The energy required to build a probe with a wavelength that's small is not just large. It exceeds anything we can build, anything we could realistically dream of building, by an almost incomprehensible margin. But the energy problem is only half the story. Because energy at that scale does something terrifying. And that is where physics stops being an engineering problem and becomes something far more disturbing. A camera cannot photograph something smaller than its own lens. A fishing net with 12-inch gaps catches nothing smaller than 12 inches. Every tool in existence has a minimum resolution, a finest detail it can capture, set by its own physical size. Light waves operate under exactly the same constraint. When light travels, it moves in waves. Think of the surface of a calm lake after you drop a stone. Rings spread outward in circles, each ring representing one full cycle of the wave. The distance between two rings is the wavelength. Small wavelength means the rings are packed tight together. Large wavelength means they are spread far apart. When a wave encounters an object, what happens next depends entirely on how the object's size compares to the wavelength. If the object is large compared to the wave hits it and bounces back, carrying information about the object's shape. If the object is small compared to the wave simply bends around it and continues on its way, as if the object were not there at all. The small object leaves no impression on the wave whatsoever. This is not a flaw in our instruments. It is a fundamental property of waves, any waves in any medium. You cannot get around it by building a better detector or a more precise sensor. The wave itself does not interact with objects smaller than its own wavelength. There is no information to capture because no information was ever generated. Radio waves have wavelengths that range from a few inches to several miles. They pass through walls and carry audio signals, but they are useless for seeing fine structure. Your FM radio can receive a signal from a tower 30 miles away, but it cannot tell you what your wall is made of at the atomic level. Visible light has wavelengths measured in hundredths of an inch, which is why your eyes can see detail far beyond what radio can offer. Ultraviolet light has even shorter wavelengths and reveals detail your eyes cannot detect. X-rays go shorter still. Each step down in wavelength opens up a new layer of reality that was previously invisible, and each step requires more energetic, more penetrating waves. The atom is roughly 1/10 billionth of a meter wide. To image it, scientists use wavelengths in the same range. A proton, packed inside the atom's core, is about 100,000 times smaller than the atom itself. Seeing a proton requires a wavelength 100,000 times shorter than what works for atoms. Now scale this all the way down to the Planck length. The Planck length is so much smaller than a proton that the comparison barely fits in language. If you started with a proton and wanted to reach the Planck length, you would need to shrink by a factor so enormous that fitting it into a sentence requires losing all intuition about what numbers mean. To probe at that scale, your measurement tool needs a wavelength matching that distance. A wave that's short carries an amount of energy that triggers something else entirely, something that Max Planck's equations could not have warned about on their own, something that requires a different branch of physics to explain. And that branch of physics was going to change everything about what measurement even means. Energy and wavelength are locked in a relationship that runs through all of physics like a hidden spine. When Max Planck fixed his blackbody equations, he discovered something that felt strange at the time, but has since been confirmed millions of times over. Energy does not flow in smooth streams. It travels in packets, discrete chunks, and the size of each chunk is tied directly to the frequency of the wave carrying it. Frequency and wavelength are opposites of each other. A short wavelength means the wave cycles very rapidly, which means high frequency. A long wavelength means slow cycles and low frequency, and Planck's discovery said that higher frequency means each packet of energy is bigger. Picture it this way. Imagine ocean waves rolling toward a beach. Long, slow waves carry a gentle push. Short, fast, choppy waves carry a violent punch. A surfer riding a long swell can drift comfortably to shore. A wave with half the wavelength arrives twice as often and hits with twice the energy per strike. The connection between wave size and energy delivery is real and physical. For light, this relationship is exact. Visible red light has long wavelengths and carries relatively low energy per photon. Blue light has shorter wavelengths and carries more energy. Ultraviolet light, shorter still, carries enough energy per photon to damage skin cells, which is why sunburn happens. X-rays carry even more and can penetrate flesh. Gamma rays, with the shortest wavelengths in the common spectrum, carry enormous energy per photon and are deadly in large doses. Every step toward a shorter wavelength means every single particle of that wave carries more energy. This is inescapable. You cannot build a short wavelength probe that is gentle. The wavelength and the energy are tied together, shrink one and the other climbs automatically. To probe the Planck length, you would need a wavelength matching that distance. The energy each particle of that probe would carry is staggering. Scientists have calculated the number precisely. Reaching the Planck scale would require concentrating roughly 2 billion joules of energy into a single probe particle. 2 billion joules is approximately the energy released by half a ton of dynamite. packed into something far smaller than a proton. At everyday scales, this trade-off is manageable. Building bigger accelerators handles the energy demands for proton-scale physics, but the Planck length is so incomprehensibly smaller than a proton that the energy required jumps far beyond any accelerator ever imagined. The largest accelerator humans have built barely reaches proton scale. Reaching Planck scale would require a machine with a circumference measured in light years. And even if you somehow built that machine, something else would go wrong. Something that has nothing to do with engineering. Something that physics itself enforces. When you concentrate that much energy into that tinier space, a new force enters the calculation. One that was absent from every measurement made at larger scales. One that turns the act of measuring into an act of destruction. The force that curves space around planets and holds galaxies together just became the biggest obstacle in the universe. Quantum mechanics was born out of discomfort. Scientists in the early 20th century kept running into results that made no sense under classical physics. Atoms should collapse. They did not. Light should behave like a wave always. Sometimes it behaved like a particle. Energy should flow smoothly. It arrived in chunks. Every experiment that probed the very small returned answers that broke the rules everyone thought were permanent. The solution was quantum mechanics, a completely new framework for understanding how energy, matter, and space behave at tiny scales. And one of its most powerful ideas is called the uncertainty principle. Werner Heisenberg published this idea in 1927. It states something radical. The position of a particle and its momentum cannot both be known precisely at the same time. Measure one with perfect accuracy, and the other becomes completely fuzzy. This is not a flaw in instruments. It is not a problem with the precision of our detectors. It is a property of reality itself. Here is the physical reason. To measure where a particle is, you have to interact with it. You send a photon at the particle. The photon bounces back and tells you the location, but the act of bouncing changes the particle's momentum. You disturbed it just by looking. A gentler probe changes the momentum less, but gives you less precise location information. A sharper probe nails the location but kicks the momentum all over the place. You can never win both at once. Sharper location measurement always means wilder momentum uncertainty. And momentum is directly tied to energy. Uncertain momentum means uncertain energy. Push the location measurement down to the Planck scale and the energy uncertainty explodes. This means any attempt to pin down a position at the Planck length forces the energy in that tiny region to fluctuate wildly. The uncertainty in energy becomes so vast that enormous amounts of energy appear and disappear in that space unpredictably. The region becomes energetically violent, seething with fluctuations that dwarf anything seen at larger scales. Think of it like trying to hold a garden hose aimed at a single target while standing on a trampoline. The more precisely you want to point, the harder it becomes because the surface keeps moving under you. Now imagine the trampoline bouncing more violently the harder you try to stabilize. The act of aiming creates the instability. At ordinary scales, these quantum fluctuations are tiny and ignorable. The uncertainty in an electron's position still leaves it clearly inside an atom. At the Planck scale, the fluctuations become so large they swamp everything. There is no stable background to measure against. The energy uncertainty alone is catastrophic. And here is where something surprising happens. Energy and mass are the same thing, just in different forms. A region seething with that much energy is, for all practical purposes, packed with enormous mass in an incredibly small volume. Einstein's equations have something to say about enormous mass packed into an incredibly small volume, and what they say is not something any measurement can survive. Werner Heisenberg was 25 years old when he changed the rules of reality. He had been puzzling over atomic spectra, the precise patterns of light that atoms emit when heated. The patterns were real and measurable, but classical physics had no explanation for them. Heisenberg decided to ignore what atoms looked like and focus purely on what could be observed, the light they emitted. He built equations based on measurements alone, stripping away all the invisible machinery underneath. What came out was startling. The math worked beautifully, but it required something strange, that certain pairs of physical properties could never be precisely known at the same time. The more precisely you knew one, the more uncertain the other became. Position and momentum, energy and time. Each pair existed in a kind of permanent negotiation, where precision in one always came at the cost of blurring in the other. Heisenberg's principle is often explained as a problem of clumsy instruments, the idea that we simply disturb things when we look at them. But that explanation sells it short. The uncertainty is deeper than that. A particle genuinely does not have a precise position and a precise momentum simultaneously. Both values exist in a smeared range until a measurement forces one to take a definite value, and forcing one to crystallize automatically blurs the other. This matters enormously for the Planck length problem. To locate something at the Planck scale, you are demanding an almost perfectly precise position, a measurement that pins down location to within 1 Planck length. The uncertainty principle responds by making the momentum of whatever probe you use wildly unpredictable. Wildly unpredictable momentum means wildly unpredictable energy. The energy in that tiny region swings between enormous values without warning. These are not small fluctuations. At the Planck scale, the energy swings are so massive that they generate gravitational effects, real, significant distortions in the geometry of space. The region you are trying to measure becomes a churning storm of energy so intense that the space inside it warps and bends. Imagine trying to measure the width of a soap bubble while standing in a hurricane. The bubble does not hold still. The wind itself becomes part of the measurement, distorting the very thing you are examining. Now imagine that the harder you try to measure, the stronger the hurricane gets. That is the situation at the Planck scale. Heisenberg's principle does not offer a workaround. It is not a temporary limitation while we wait for better tools. It is a law built into the structure of the universe, as solid as the speed of light. Every attempt to beat it fails for the same reason. The universe does not allow simultaneous perfect knowledge of both position and momentum. That prohibition is absolute. What this means practically is that any probe capable of resolving Planck scale distances will always carry violent energy fluctuations. Those fluctuations will always warp the local space, and warped space with a violent energy injection at a single point has only one possible destination under Einstein's equations. A destination that makes returning data completely impossible. Something far darker is waiting at the end of this chain, and it forms automatically the instant you try. Albert Einstein published his general theory of relativity in 1915, and it reset every assumption humans had about what gravity actually is. Before Einstein, gravity was a force. Isaac Newton had described it that way. Two masses attract each other across space, pulling toward each other with a strength that depends on their masses and the distance between them. Newton's equations worked brilliantly. They predicted planetary orbits with stunning accuracy. For 200 years, nobody found a reason to doubt them. Einstein found a reason. His insight was that gravity is not a pulling force between objects. Gravity is the shape of space itself. Mass does not reach across empty space and tug at other objects. Mass curves the space around it. Objects moving through that curved space follow the curves, which from the outside looks like attraction, but is actually geometry. Imagine placing a bowling ball on a stretched rubber sheet. The sheet sinks under the ball's weight, creating a curved depression. A marble rolled near the bowling ball follows the curve of the sheet and spirals inward. The marble is not being pulled by an invisible force. It is following the shape of the surface. That is gravity. Space is the rubber sheet. Mass creates the depression. Everything moving nearby follows the curve. Now here is the piece that matters for the Planck length. Einstein also showed that mass and energy are interchangeable. They are different forms of the same thing. A massive object curves space. An object with enormous energy does the same. The equation connecting them is the most famous in science. Energy equals mass times the speed of light squared. A small amount of mass can release a staggering amount of energy. Conversely, a large amount of energy is equivalent to a significant amount of mass for the purposes of bending space. This means energy curves space. Energy creates gravity. Energy, if concentrated enough, can warp the local geometry of space-time as dramatically as any massive object. At everyday scales, the energy we deal with is so small compared to the masses of planets and stars that its gravitational effect is unmeasurable. But at the Planck scale, something different happens. The energy required to probe this distance is not just large in engineering terms. It is large enough, when packed into a volume that small, to curve space-time dramatically. The local gravity of the probe itself becomes the dominant force in the region. A single particle carrying the energy needed to see the Planck length would generate a gravitational field powerful enough to collapse the space around it. The geometry in that tiny region would buckle under the weight of the energy you introduced, and buckled geometry with a violent energy source at its centre follows a path that Einstein's equations predict with perfect clarity. The space collapses inward. The measurement creates something that swallows everything you sent in to measure, and that something has a name everyone recognises, even if few people understand what waits inside it. Every physical theory has a breaking point. Push the conditions far enough outside the normal range, and the equations stop giving sensible answers. They spit out zeros in denominators, infinities where finite numbers should be, contradictions that cannot all be true at once. These mathematical disasters are called singularities, and they are usually signs that you have pushed the theory past its limits. The Planck length is where two completely different theories, quantum mechanics and general relativity, both hit their limits at exactly the same place, at exactly the same moment, and in exactly opposite directions. General relativity describes the large-scale structure of the universe with breathtaking precision. Black holes, gravitational waves, the bending of light around massive objects, the expansion of space itself, all of these follow from Einstein's equations. The theory works at astronomical scales with extraordinary accuracy. Quantum mechanics describes the behaviour of particles at the smallest scales we can probe. The way electrons orbit atoms, the way light carries energy in discrete packets, the way particles tunnel through barriers they classically should not be able to cross. Quantum mechanics has been tested more thoroughly than almost any theory in science and has never failed a test. Apply both theories to the same situation at the Planck scale, and they give completely different, completely irreconcilable answers. The mathematical output of each theory invalidates the other. General relativity predicts that extreme energy concentration causes catastrophic gravitational collapse. Quantum mechanics predicts that the energy in a confined region of that size fluctuates wildly and unpredictably. The two descriptions cannot both be right, and combining them produces equations that collapse into meaningless infinities. Here is the concrete version of what the math says. Take the energy required to probe at the Planck length. When you concentrate that energy into a volume that small, the density of energy per unit volume reaches a critical threshold. General relativity has a precise name for what happens past this threshold. The math says the space curves so severely that it closes on itself. A boundary forms around the energy, beyond which nothing can escape. The gravitational grip exceeds the speed of light. At the same moment, quantum mechanics says the position of the energy is fundamentally uncertain. The energy does not sit in one spot. It fluctuates across a range of values and positions. The more precisely you try to localize it, the more violently it fluctuates. These two descriptions cannot coexist. Relativity demands a specific curved geometry around a specific energy concentration. Quantum mechanics says there is no specific energy concentration, only probabilities. Push both theories to the Planck scale simultaneously, and the mathematics of the universe returns an error message. Physicists call this regime quantum gravity, a place where both theories should apply, but neither one alone tells the full story. A theoretical framework that unites them does not yet exist. Every attempt to build one either breaks quantum mechanics or breaks relativity, and the practical result of this mathematical failure is something visible and dramatic. A microscopic black hole, formed instantly, from the very act of trying to look. A black hole forms when mass or energy gets packed into a small enough space that nothing can escape the gravitational pull. Even light, travelling at 186,000 miles per second, cannot outrun it. There is a boundary around every black hole called the event horizon. Cross it in any direction and you cannot come back. Physics allows entry, it forbids exit. Black holes in space form from dead stars. A star massive enough, at the end of its life, collapses inward under its own gravity. The collapse is so extreme that the core is crushed past the point where normal matter can push back. If the remaining mass is above a critical threshold, the collapse continues until a singularity forms and an event horizon seals around it. Black holes in space are enormous. The smallest known stellar black holes are several miles across. At the Planck scale, the same process happens on a scale so tiny it has no visual parallel. The probe you send in to measure the Planck length carries enormous energy. That energy, concentrated into a volume the size of the Planck length, generates a gravitational field intense enough to curve spacetime past the critical point. The energy folds space around itself. An event horizon forms. A black hole, microscopic beyond imagination, blinks into existence at the exact moment your measurement was supposed to complete. The probe that was supposed to bounce back and carry information home is now inside an event horizon. It cannot return. The light or particle that was supposed to tell you what the Planck scale looks like is trapped, crushed, absorbed into the collapsed geometry of space that your own measurement created. You sent a probe in. The probe destroyed the space it was examining. A black hole formed and swallowed all the information. The detector outside receives nothing. This is not a failure of a specific instrument or a specific technique. It is a structural feature of the universe. Every possible measurement method at this scale produces the same result. Any probe with enough energy to resolve Planck distances automatically creates a black hole. Any probe without enough energy cannot resolve Planck distances at all. There is no middle ground. The universe closes off both paths simultaneously. Scientists call this a self-defeating measurement. The more precisely you aim, the more catastrophically the measurement destroys itself. The tool cannot help revealing the scale, and revealing the scale cannot help destroying the tool. What makes this deeply strange is that the universe is not passive here. The formation of the black hole is not a side effect you could engineer around. It follows directly from the same laws that make the measurement necessary in the first place. The laws of gravity and quantum mechanics together build the wall and enforce it simultaneously. The space you are trying to see no longer exists in any measurable form. It collapsed, and if any data at all survived, it cannot escape the event horizon to reach you. But this raises an even deeper question. If the space collapses every time you try to measure it, does that mean smaller distances are simply unphysical? Does space actually have a minimum structure? The answer that follows is one of the strangest ideas in all of science. The event horizon is the point of no return. It is not a physical surface. You cannot see it, touch it, or detect it directly. It is a mathematical boundary in space where the escape velocity equals the speed of light. Inside this boundary, the speed required to escape the gravitational pull exceeds the fastest speed anything in the universe can travel. Light itself, the fastest thing that exists, cannot climb out. Anything that crosses into the event horizon stays there permanently. This property makes black holes the perfect information destroyers. When scientists probe tiny scales, the goal is always the same: send something in, get something back. The returning signal carries data about what it encountered. A photon bouncing off an atom returns with a shifted wavelength that tells scientists about the atom's structure. A particle deflected by a proton returns with an angle that reveals something about the proton's interior. All measurement in physics works on this principle: send a probe, receive the echo, decode the echo. At the Planck scale, the echo never arrives. The probe enters the region, the black hole forms, and the probe is gone. The event horizon seals around it. No echo travels back, no signal escapes. The detector waiting on the outside receives absolute silence. The measurement returns zero information, not because the probe found nothing, but because the probe was swallowed before it could report. This is physically different from simply having a bad detector. A bad detector might miss weak signals. A better detector might catch them. The event horizon does not care how sensitive your detector is. Information trapped inside a black hole obeys physics laws that make retrieval theoretically impossible under the standard model. Stephen Hawking later proposed that black holes do eventually radiate energy and information in a form called Hawking radiation, but this radiation is thermal and scrambled. Any information encoded in the original probe is lost inside the black hole's interior, mixed beyond recovery with the chaotic structure of the collapsed region. Even if you waited for the microscopic black hole to eventually evaporate, the information that came out would be so thoroughly scrambled that reconstructing the original measurement would be impossible. The universe at the Planck scale operates a one-way door. Information goes in. Information does not come out in any usable form. Every other limit in science is a practical limit. We cannot see past the edge of the observable universe because light from beyond has not had time to reach us yet. We cannot see the interior of the sun because the material is too dense and opaque. We cannot see individual atoms with the naked eye because visible light waves are too large. All of these limits can be worked around with the right tools, the right wavelengths, the right instruments. The Planck scale event horizon is different. It is a law-enforced boundary. The tools that would bypass it are the same tools that create it. So the question physicists were forced to ask was radical. If every attempt to see below this scale produces a black hole, and every black hole returns no data, maybe there is simply nothing below this scale to see. And if space has a minimum size, then space is something completely different from what we assumed. Every limit in everyday life has a workaround. Speed limits can be broken. Sound barriers were thought unbreakable until aircraft punched through them. The idea that humans could never leave Earth's atmosphere seemed absolute until it stopped being absolute. Human history is full of barriers that fell apart when technology or understanding advanced far enough. The Planck length is not that kind of barrier. It does not sit at the edge of current technology waiting for a smarter machine to push past it. It sits at the edge of physical law, enforced by the same equations that make the universe work at every scale above it. The barrier is not a door, it is the floor of the building. Below it, there is no building. Here is what this means precisely. Geometry requires distances to be meaningful. To draw a line between 2 points, both points have to have a definite location. To measure an angle, the sides of the angle have to extend through space that behaves consistently. All of mathematics and physics builds on the assumption that space is a smooth, continuous structure where these operations always work. At the Planck scale, that assumption fails. 2 points separated by less than 1 Planck length cannot be distinguished from each other. The quantum fluctuations at that scale are so violent that any 2 locations within a Planck length of each other are indistinguishable in practice and possibly in principle. The very concept of being between 2 locations stops functioning. There is no meaningful halfway point between 2 spots that are already at the Planck limit. Distance requires space to be divisible. At the Planck scale, space stops being divisible. Asking for something smaller is like asking for half a pixel on a screen. Below that pixel, the screen has nothing. The pixel is the finest grain of the image. The Planck length may be the finest grain of space. This conclusion is not wild speculation. It follows directly from combining the mathematics of quantum mechanics and general relativity. Both theories, pushed to their extreme, predict that the structure of space-time becomes violently unstable and undefined at this scale. The smooth stage on which all of physics plays out becomes something unrecognizable. A region of space smaller than the Planck length would have so much quantum energy churning through it that it could not be called space in any useful sense. It would not be a location, it would not be a volume. The ordinary vocabulary of physics would have no words that apply. And here is what that means for the question everyone eventually asks. What is below the Planck length? The answer is that the question is grammatically correct but physically empty. Below the Planck length is not a smaller region. Below the Planck length is the same kind of territory as north of the North Pole. The compass still works. The words still make sense in English. But the physical reality it points to does not exist. The universe does not extend infinitely downward. It has a bottom. And the man who proved this most rigorously was not Max Planck. He was a physicist barely anyone outside the field has heard of, and his proof was almost ignored when it arrived. Geometry is the language of shape. It describes how distances work, how angles add up, how surfaces curve. Every map, every blueprint, every calculation involving physical location depends on geometry working correctly. The geometry we use every day was formalized by ancient Greek mathematicians and holds up perfectly well at every scale humans can directly observe. At the Planck scale, this language stops describing anything real. To understand why, start with something familiar. Draw a triangle on a flat piece of paper. The 3 interior angles always add up to 180 degrees. This is a law of flat geometry, and it works perfectly on any flat surface. Now draw the same triangle on the surface of a sphere, like the surface of the Earth. Start at the equator, walk to the North Pole, turn 90 degrees, walk back to the equator, turn 90 degrees again, and walk back to your starting point. That triangle has 3 90-degree corners, which add up to 270 degrees. The geometry of a curved surface is completely different from flat geometry. General relativity tells us that space is not flat. Mass and energy curve it. Near a black hole, the geometry is so extreme that ordinary distance and angle calculations are useless. Space behaves in ways that flat geometry cannot capture. At the Planck scale, the curvature problem becomes extreme beyond anything near a black hole. The violent energy fluctuations predicted by quantum mechanics warp the local geometry continuously and randomly. The curvature is not stable. It does not settle into a definable shape. It churns and jumps and twists in ways that make geometry impossible to apply. Imagine trying to use a ruler on a surface that ripples and tears and folds faster than the ruler can touch it. The ruler is not broken. The surface simply does not hold still long enough for the measurement to mean anything. At the Planck scale, space itself is that surface. The ruler, the measurement, the concept of a stable location all dissolve in the violence of the fluctuations. Physicists describe this condition as the breakdown of classical spacetime. The smooth, continuous background on which all of physics is usually written simply does not exist here. This is why the Planck length is not described as the smallest distance we can measure. It is described as the scale at which the concept of distance stops being meaningful. There is a difference between measuring something difficult and measuring something that has ceased to be a coherent thing. Position requires stable geometry. Stable geometry requires spacetime to have a definable shape. Below the Planck length, spacetime has no definable shape, so position, location, and distance become words without reference. They point at nothing. The question how far is it between these 2 points below the Planck length cannot be answered because the points themselves cannot be defined. Every theory of physics that has ever been written assumes geometry works. Classical mechanics assumes it. Quantum mechanics assumes it. General relativity assumes it but predicts the circumstances where it fails. At the Planck scale, all 3 assumptions collapse simultaneously. Something completely different must take over. Some new framework, something beyond existing physics, must describe what happens in this regime. That framework does not yet exist, but some of the most ambitious theories ever attempted are trying to build it, and one of them starts by imagining that space is not smooth at all. Stand at the North Pole. Face north. What do you see? Every direction from the North Pole is south. There is no north from the North Pole. The concept of north requires a reference point above you and at the top of the planet. No such reference exists. The compass needle spins uselessly. The question which way is north is not just unanswerable, it is the wrong question for that location. The vocabulary has failed before the conversation started. The Planck length creates the exact same situation for the concept of distance. When physicists ask what lies below the Planck length, they are using the word below as if smaller distances are a direction you can travel in, as if the scale of size is a road with more road below the last mile marker. It feels that way because every scale we have ever explored has had a smaller scale waiting beneath it. Organisms have cells. Cells have molecules. Molecules have atoms. Atoms have nuclei. Nuclei have protons. Protons have quarks. Each level opened a new one below it. The Planck length appears to end this pattern. Below it, the machinery that makes below work as a concept stops functioning. Space does not extend further. Space does not organize into smaller units. Space loses its spatial character entirely at this boundary. This means the question what is smaller than the Planck length is grammatically valid, but physically empty. It sounds like a question about the universe, but actually points at nothing the universe contains. It is the North Pole problem applied to the fabric of reality. Scientists are careful to distinguish between two kinds of limits. A practical limit is one we cannot currently overcome, but might overcome in the future with better tools. A fundamental limit is one that arises from the basic structure of physics and cannot be overcome regardless of technology. The speed of light is a fundamental limit. No engineering advance will ever allow matter to travel faster. The Planck length is proposed to be in the same category. If this is correct, then the universe does not extend downward infinitely. The infinite divisibility of space is an illusion produced by operating at scales where the limit has not been reached. At every scale humans have explored, cutting things smaller worked. At the Planck scale, cutting things smaller produces a black hole and returns nothing. The cut cannot be made. The implications cascade upward. If space has a minimum size, then it is granular at the base. A fabric woven from finite units, each roughly the size of the Planck length. The smooth, continuous space described in almost all of physics would be an approximation, valid at large scales, but ultimately a smoothed-out version of something much more discrete at the bottom. What those discrete units look like, how they connect, what rules govern them, nobody knows with confidence. Physics has candidate answers, ambitious, creative, mathematically intense candidate answers. But none of them have been confirmed by any experiment yet. The man who first proved mathematically that this wall had to exist was almost entirely overlooked when he published his proof. For years, his results sat in a journal while physics moved on to other problems. Only later did the field catch up to what he had figured out early. Most stories about the Planck length skip past Charles Alden Mead entirely. His name does not appear in popular science books. He has no dramatic biography attached to his discovery. He was a careful, methodical physicist who published a paper in 1964 and then watched the field largely ignore it for decades. But what Mead proved was the first rigorous mathematical demonstration that measuring anything below a fundamental minimum length was physically impossible. He was the first to combine both gravity and quantum mechanics into a single argument and show exactly where they intersect to form an absolute wall. Before Mead, the Planck length was an interesting curiosity. Planck himself had noted that his combination of fundamental constants produced a unit of length, but had not made claims about its physical meaning. Other physicists glanced at it, found it interesting, and moved on. The number sat in the equations without a story attached to it. Mead attached the story. He started from the uncertainty principle. To pin down the position of a particle to within some distance, you need a probe with a short enough wavelength to resolve that distance. Shorter wavelength, higher energy, larger momentum transferred to the probe. So far, this was standard quantum mechanics, nothing new. Mead then asked a question almost nobody had asked before. What does gravity do to this measurement? The probe carries momentum. Momentum means energy. Energy curves space-time. At everyday scales, the gravitational effect of a probe's energy is so tiny it can be ignored completely. Mead calculated exactly how tiny, and then kept shrinking the target distance to see what happened to the gravitational contribution. As the target distance shrank, the required probe energy grew. As the probe energy grew, the gravitational distortion it created grew. Meade tracked both simultaneously and found that they met. There was a specific distance at which the gravitational distortion caused by the probe became comparable in size to the distance being measured. At that point, the measurement destroyed its own target. That specific distance was the Planck length. Meade wrote this up carefully, submitted it, and it was published. The physics community read it, acknowledged it as correct, and largely set it aside. The consensus at the time was that quantum gravity effects were not something the field needed to address urgently. The tools to probe even a fraction of this distance did not exist, and showed no signs of existing soon. The result felt academic. Decades later, as physicists began to wrestle seriously with quantum gravity and the deep structure of space-time, Meade's paper resurfaced. Scientists realized he had proven the essential result first, using clean and direct mathematics. His argument remains among the clearest explanations of why the Planck length is a physical wall and not just a small number. Here's a reminder that physics sometimes gets the right answer and files it away under unfinished business. The result Meade proved rested on the behaviour of the probe and the target. But to feel the full weight of what the Planck length means, you have to confront its size directly. And the numbers involved are so extreme that no everyday comparison quite captures them. The next comparison might be the most disorienting fact in all of physics. An atom is already incomprehensibly small. A human hair is roughly 100,000 atoms wide. Stack 100,000 atoms side by side, and you would still barely cover the width of a strand of hair sitting on a table. If you tried to count the atoms in a single grain of sand, and you counted one per second without stopping, it would take longer than the current age of the universe to finish. That is how many atoms fit in a grain of sand. And the Planck length is smaller than an atom by a factor that makes the atom-to-hair comparison look trivial. An atom is roughly 100 quintillion times larger than the Planck length. Write that number out. 100 followed by 18 zeros. That ratio is not a distance comparison between two small things. It is a comparison between an almost invisibly small thing and something so many orders of magnitude smaller that the math requires exponential notation just to write it down. Here is a comparison that might help, though it can only gesture at the actual scale. Imagine you could expand a single atom until it was as wide as the entire observable universe. The observable universe stretches roughly 90 billion light-years across. A light-year is the distance light travels in a full year, moving at 186,000 miles per second. The observable universe is so large that human intuition breaks completely when trying to picture it. Expand one atom to that size. Inside that atom, expanded to fill everything we can see in all directions, the Planck length would be approximately the size of a single grain of sand. A grain of sand. Inside a universe-sized atom, that is the ratio. Another way to feel it, a proton. The particle sitting in the nucleus of every atom is already about 100,000 times smaller than the atom it lives in. The Planck length is roughly 100 million billion times smaller than a proton. If the Planck length were the size of a proton would be larger than the entire observable universe. These comparisons do not land the way they should, because human minds evolved to navigate a world of trees and rocks and distances measured in miles. Our intuition has no category for numbers this large. We can write them. We can say them. We cannot feel them. What we can feel is the implication. Every single experiment humans have ever performed, every particle accelerator, every atomic measurement, every observation at any scale happens at distances billions of times larger than the Planck length. We have never scratched the surface of this scale. Our best machines are nowhere near it. The Planck length is not the next level down. It is the final level, sitting so far below our current reach that the gap between us and it is larger than the gap between us and the observable universe. And yet, at that unimaginable depth, the universe enforces a rule that may mean space itself has a pixel size, a resolution limit, a granularity baked into reality from the very beginning. What that granularity actually looks like, what it means for the structure of space, is where the story takes its strangest turn yet. Numbers like 100 quintillion times smaller collapse inside the brain without leaving a mark. So physicists and science communicators have tried for decades to build comparisons that stick. Comparisons that use objects a person can actually see and touch. The results are always somewhere between humbling and disturbing, because no comparison quite lands. The scale is simply too extreme for any image to carry the full weight of it. Here is the most famous one. Take a single atom. Expand it. Keep expanding until that atom is as large as the entire planet Earth, roughly 8,000 miles across. At that magnification, where is the Planck length? It would be roughly the size of a single proton inside that Earth-sized atom. A proton is already tiny. Inside a real atom, the proton sits in the nucleus, which itself takes up a fraction of the atom's total volume. Physicists describe the atom as mostly empty space, a tiny dense nucleus surrounded by a cloud of electrons at enormous relative distances. If the atom were a football stadium, the nucleus would be a marble on the 50-yard line. At Earth scale, after expanding the atom to 8,000 miles wide, the nucleus of that expanded atom would be somewhere around the size of a football field, and the Planck length inside it would be the size of a proton sitting somewhere in that football field. A proton inside a football field-sized nucleus inside an Earth-sized atom. That is the Planck length. But even this comparison understates it, because the comparison uses the atom to Earth expansion, which is itself an enormous ratio. The number of times you would need to stack Planck lengths to reach the size of a single atom is so large that if each Planck length were 1 inch, the stack would be far longer than the distance from Earth to the edge of the observable universe. This is why physicists stop trying to visualize it directly and focus instead on what the math says must happen there. The math is clear. The behavior at that scale is predictable from the laws we already have, even if those laws break down right at the boundary. And what the math says is unsettling enough without needing a picture. At this scale, space does not sit still. It does not behave like a quiet, empty container. The quantum fluctuations that the uncertainty principle demands at this scale make the very fabric of space violently unstable. A physicist named John Archibald Wheeler imagined what this looked like and gave it a name that has stuck ever since. He called it quantum foam. And what he described is one of the most visually strange ideas in all of science. Space, at the Planck scale, churns, it boils. It twists into tiny structures and collapses them again, faster than any clock can tick. The smooth emptiness you associate with space is a large-scale illusion. Zoom in far enough, and the quiet stage becomes a seething storm. What that foam actually looks like, and what it means for the nature of time itself, is where this story accelerates into territory that even physicists find genuinely unsettling. John Archibald Wheeler spent his career asking questions that made other physicists uncomfortable. He worked alongside some of the greatest minds of the 20th century. He helped develop nuclear physics. He coined the term black hole at a time when most scientists still refused to believe such objects could exist. He pushed quantum mechanics into territory most of his colleagues considered too speculative to touch. Wheeler was not reckless. He was thorough and mathematically rigorous. He simply refused to stop asking what happened at the edges. In the 1950s, he turned his attention to what space itself might look like at the smallest possible scales. He already understood that quantum mechanics forced energy to fluctuate wildly in tiny regions. He already understood that Einstein's equations tied energy to the curvature of space-time. He put those two ideas together and asked the obvious question that almost nobody else was asking. If energy fluctuates violently at the Planck scale and energy curves space, what does space look like down there? His answer was quantum foam. Imagine the surface of the ocean viewed from 30,000 feet above. From that height, the ocean looks flat, smooth, and calm. Drop to 100 feet, and you start to see swells and waves. Drop to 10 feet, and the surface is clearly churning. Stand in the water and waves crash over you. Zoom in to the scale of a single droplet, and the water is a constantly shifting dynamic surface with no stable geometry at all. Space, Wheeler proposed, behaves the same way. At everyday scales it looks smooth and stable, a quiet background for events to happen against. But zoom in toward the Planck length and the quantum fluctuations that quantum mechanics demands begin to dominate. The geometry of space-time churns. Tiny structures form and collapse. Connections appear between distant points and vanish again. The quiet emptiness of space dissolves into something more like boiling water than a still surface. Wheeler called these structures wormholes, tiny tunnels through space-time that open and close at the Planck scale in fractions of a second. These are not the wormholes of science fiction, large, stable passages between distant galaxies. These are microscopic, fleeting, forming and dissolving so rapidly that no information could ever travel through them before they vanish. They exist as a consequence of the mathematics, not as tunnels anyone could use. The foam is not static, it is a dynamic, constantly changing structure. No two moments at the Planck scale look the same. The geometry of space reinvents itself continuously, producing new configurations of curvature and then destroying them before they can be measured. This idea has never been confirmed experimentally. The scale is so far beyond our instruments that no telescope or particle accelerator can observe quantum foam directly. But the mathematics that predicts it follows from firmly established physics. The uncertainty principle combined with general relativity produces quantum foam as a logical consequence. Several astrophysicists have searched for indirect evidence by looking for tiny distortions in light travelling billions of light years across a foamy space-time. The results so far are inconclusive. What Wheeler's vision tells us is something profound about the nature of reality. The smooth, continuous, stable space we experience every moment of our lives may be a statistical average, an approximation that emerges from something wildly unstable and granular at its base. The calm ocean viewed from 30,000 feet. And if the fabric of space is churning at its base, time at that scale may be doing something even stranger. Time moves forward. Every human being who has ever lived has experienced this as an absolute fact. Yesterday happened before today. Today happens before tomorrow. Causes come before effects. Memory points backward. Anticipation points forward. The arrow of time feels like the most basic feature of reality, more obvious than gravity, more certain than anything. At the Planck scale, that arrow dissolves. To understand why, start with what time actually is in physics. Einstein's relativity showed that time is not a separate thing flowing alongside space. Time and space are woven together into a single four-dimensional structure called space-time. Moving through space affects your experience of time. Gravity warps time as well as space. A clock at the base of a mountain ticks slightly slower than a clock at the summit because the stronger gravitational field near the ground stretches time. These are measured, confirmed effects, not speculation. Time in relativity is a dimension, just like the three spatial dimensions. The difference between the past and the future is a feature of the geometry of space-time, an arrow built into the structure of the four-dimensional fabric. At the Planck scale, that fabric stops having a stable structure. The quantum fluctuations Wheeler described in his quantum foam model do not just churn the spatial dimensions, they churn all four dimensions simultaneously. The geometry of spacetime at the Planck scale fluctuates so violently that the distinction between a spatial direction and a time direction becomes blurred. The four dimensions of spacetime mix together unpredictably. The clear separation between forward in time and backward in time that defines the arrow of time at everyday scales loses its meaning when the geometry itself is churning. Physicists describe this as the breakdown of causal structure. Causality requires that causes precede effects. Precedence requires a clear ordering of events in time. Clear ordering requires time to have a definite direction. At the Planck scale, time loses that direction. Events at this scale cannot be placed in a clear sequence. The vocabulary of before and after stops applying. This is not a theory that time runs backward below the Planck scale. It is a statement that the concept of temporal ordering becomes undefined. Before and after are categories that require time to behave like a dimension with a clear orientation. At the Planck scale, time behaves like something else entirely, something for which no word in everyday language is adequate. If you tried to describe two events at the Planck scale and asked which one happened first, the question would return no answer. The events are not simultaneous in the usual sense. They are not sequential in either order. They exist in a regime where the normal rules of sequencing do not apply. For humans living at the scales we inhabit, this has no practical consequence. Time flows forward reliably at every scale we will ever interact with. The breakdown of causal structure at the Planck length is sealed away from ordinary experience by the same vast gap of scale that separates us from quantum foam. But the implication is staggering. The forward flow of time, the single feature of reality that shapes every moment of human experience, may be an emergent property of space-time geometry, a feature that arises at large scales from something deeper that has no time direction built in at all. And if space-time itself emerges from something more fundamental, physics needs a theory of what that something is. 3 candidates have been proposed. Each one reimagines the fabric of reality from the ground up. The first one involves strings. Sometime in the 1960s, a group of physicists working on the strong nuclear force stumbled onto an equation that described particles as tiny vibrating strings. The idea was quickly abandoned for that purpose when a better theory came along. But the mathematics of vibrating strings kept generating interesting results, and a small group of theorists refused to let it go. By the 1980s, that stubborn minority had developed something remarkable, a framework called string theory, which proposed that every particle in the universe, every electron, every quark, every photon, is a single vibrating loop of energy. The particle is a string. Different vibration patterns produce different particles with different properties. An electron vibrates one way, a quark vibrates another, a photon vibrates differently still. The entire zoo of particles in physics reduces to one object playing different notes. The size of each string was predicted by the mathematics, and the size the equations gave was the Planck length. This means string theory gives the Planck length a specific physical interpretation. Strings at the Planck scale are the smallest possible things because strings are the most fundamental things that exist. Below the Planck length, there is nothing smaller because there is nothing else to be smaller. The strings are the base layer. They have no internal structure to probe. They are the bottom of the stack. This elegantly explains why the Planck length functions as a minimum. Any attempt to probe below it would require probing inside a string. But a string has no inside. It is a one-dimensional object, a loop with no interior volume. The concept of looking inside a string is like asking what is on the inside of a mathematical line. Lines have length but no width. There is no inside to enter. String theory also, at least in principle, unifies quantum mechanics and general relativity. The vibrating strings naturally produce a particle called the graviton, which carries the gravitational force. Gravity emerges from the same framework as all other forces. The two great incompatible theories of physics get absorbed into one description. The problem is that string theory requires dimensions beyond the 4 we experience. Most versions require 10 or 11 dimensions. The extra dimensions are proposed to be curled up at the Planck scale, too small to detect with any current instrument. The theory also generates an enormous number of possible universes, each with different physical constants, and selecting which one corresponds to ours has proven extraordinarily difficult. String theory has made no confirmed experimental predictions that distinguish it from other theories. It remains mathematically rich, intellectually compelling, and completely unverified. Physicists continue working on it, producing new results and variations. But the experimental confirmation that would settle the debate has not arrived. A different approach to the same problem starts from a completely different angle. String theory says particles are strings. This other approach says something more radical about space itself. It says space is made of loops. Loop quantum gravity begins with a radical decision: take quantum mechanics and general relativity both seriously, exactly as they are, and force them to work together without inventing new dimensions or new fundamental objects. The result is a picture of space so different from everyday experience that it takes a moment to fully register. In loop quantum gravity, space is not a smooth, continuous background. Space is quantized. It comes in discrete chunks, the smallest of which is roughly the volume of a cube, with sides 1 Planck length long. Space is made of a network of these chunks, connected by links, forming a structure that some physicists describe as a spin network. The smooth space of our experience is an approximation that emerges when you zoom out far enough from this granular structure, the same way a photograph looks smooth from across the room but reveals individual pixels up close. This is the most literal version of the Planck length, as a pixel of reality. In ordinary photography, a pixel is the smallest unit of an image. Below the pixel level, the image has no content. You can zoom in forever, but the pixel does not divide into smaller pixels. It is the indivisible grain. Loop quantum gravity proposes that space works exactly this way. The Planck length is the pixel of the universe. Below it, there is no space to divide. The question of what exists at smaller scales has no answer, because smaller scales do not exist in the spin network. Time in this framework is also quantized. It does not flow continuously. It advances in discrete steps, each roughly equal to the time light takes to cross 1 Planck length. Between steps, there is no during. Time does not pass between ticks. The ticks are all there is. This picture of discrete time and discrete space is deeply different from the space-time of general relativity, which treats both as perfectly smooth and continuous. Loop quantum gravity must explain how the smooth space-time of Einstein's equations emerges from a granular network of chunks at the Planck scale. Researchers working in this framework have made significant mathematical progress on this question, but a complete and satisfying answer remains out of reach. Loop quantum gravity does make some predictions that differ from standard physics. It predicts specific effects on high-energy light travelling across cosmic distances. Gamma-ray telescopes studying bursts of light from explosions billions of light-years away have searched for the signature of a granular spacetime. The results have constrained the theory significantly. Some versions of the theory have been ruled out, others survive. String theory and loop quantum gravity represent two of the most serious attempts to describe physics at the Planck scale. They are not the only attempts, but they are the most developed. Neither has won the argument. Both continue generating new mathematics and new insights, and both agree on one practical fact that is sobering for anyone hoping for experimental resolution. Actually testing either theory at the Planck scale requires an instrument so enormous it staggers the imagination. The Large Hadron Collider at the European Centre for Nuclear Research is the most powerful particle accelerator ever built by humans. It sits in a circular tunnel 17 miles around, buried roughly 300 feet underground beneath the border of France and Switzerland. Building it required an international collaboration involving more than 10,000 scientists from over 100 countries. The effort took decades and cost approximately $5 billion. When it finally switched on in 2008, it smashed protons together at energies that briefly recreated conditions a fraction of a second after the Big Bang. At full power, the collider probes distances roughly 1,000 times smaller than a proton. The Planck length is roughly 100 million billion times smaller than a proton. To probe the Planck length with a particle accelerator, the machine would need to accelerate particles to energies so far beyond what the Large Hadron Collider achieves that the ratio between them is essentially incomprehensible. Physicists have done the calculation. An accelerator capable of reaching Planck energies in the same way current machines reach proton scales would need a circumference measured in light years. The distance from Earth to the Sun is roughly 93 million miles. 1 light year is almost 6 trillion miles. An accelerator with a circumference measured in light years would extend far beyond our entire solar system, stretching into interstellar space, encircling a loop of track hundreds of trillions of miles around. Building such a machine is so far beyond any conceivable technology that the calculation functions more as a proof of impossibility than as an engineering challenge. This means no experiment currently planned or realistically imaginable with any technology derived from current science will ever directly probe the Planck scale. The theoretical predictions of string theory, loop quantum gravity, and every other quantum gravity framework will remain unverifiable by direct means for the foreseeable future, and possibly forever. Physicists have not given up. They are searching for indirect tests, situations where Planck scale physics might leave a detectable fingerprint at scales accessible to real instruments. The most promising avenue involves light from distant cosmic explosions called gamma-ray bursts. These events release enormous energy across the universe, and photons of different energies travel slightly different distances if space-time has a granular structure at the Planck scale. Measuring the arrival time difference between high and low energy photons from these bursts could reveal the texture of space-time. So far, the measurements have been consistent with a smooth space-time at the scale our instruments can reach. Some versions of quantum gravity theories have been constrained or ruled out, but confirming a specific correct theory of Planck scale physics this way is enormously difficult. The signatures are subtle, and the distances involved introduce many other possible explanations for any observed differences. The honest answer is that physics has reached a frontier it may never be able to cross experimentally. The greatest mystery in science, the true nature of space and time at their most fundamental level may be permanently hidden behind an observational wall enforced by the very laws of physics. And the strangest detail about this wall is just how universal it is. Light has no mass. This is one of the first things physics textbooks say about photons. They travel at the speed of light because only massless particles can reach that speed. They carry energy and momentum but weigh nothing on any scale. A beam of sunlight hitting your skin pushes on you with immeasurable pressure, but no scale in the world would register the weight of the photons raining down on it. And yet, a photon with enough energy to probe the Planck length would carry so much energy that through Einstein's equivalence of mass and energy, its effective mass would be roughly equal to the mass of a flea. A flea weighs somewhere between 1 and 2 thousandths of a gram. It is the weight of a few eyelashes, trivially light by everyday standards. You could hold 1,000 fleas in one hand and barely feel them. At the quantum scale, however, a flea represents an almost impossibly large concentration of mass. A single proton weighs roughly 1 million billion times less than a flea. A single photon at normal energies weighs incomprehensibly less than that. A flea mass photon would carry energy so concentrated that when localized in the volume of a Planck length, its gravitational field would dwarf anything produced by any particle physics process ever observed. The energy density in that tiny volume would exceed anything that has ever been measured, by margins that make the Large Hadron Collider's achievements look like a match flame next to a supernova. This comparison lands differently than an abstract number. A flea is something you can see. You could hold one in your hand. The idea that a single particle of light, massless by nature, could carry the energy equivalent of something visible to the naked eye and small enough to jump off your arm, captures the violence of the Planck scale in a way that purely numerical comparisons cannot. That flea mass photon would of course instantly create a microscopic black hole upon trying to measure anything. The energy it carries makes the measurement self-defeating by definition. But the image is useful. It tells you something real about the scale of energy involved. It also raises a question that cuts to the heart of what the Planck length actually is. The energy of that photon is not arbitrary. It comes from combining 3 constants of nature: the speed of light, the gravitational constant, and Planck's constant. These constants were measured independently, in completely separate branches of physics, by completely different experiments. Nobody designed the combination to produce a flea's mass. Nature produced it automatically, and this leads to one of the most philosophically striking features of the Planck length. Every civilization capable of doing physics anywhere in the universe would calculate the same number, using the same constants, getting the same result. The Planck length belongs to the universe, not to humanity. Human units of measurement are human inventions. A mile is the distance it is because Romans defined it as 1,000 double paces of a marching soldier. An inch was historically tied to the length of a thumb. A second was defined as a fraction of a day, which was defined by Earth's rotation, which is a local accident of how our planet formed. Alien civilizations measuring the same distances would arrive at completely different numbers because they would have invented completely different base units. The number 5 miles is meaningless to a civilization that has never encountered humans or Earth. The Planck length is completely different. It is derived from 3 constants that are not human inventions. The speed of light is the same everywhere in the universe. The gravitational constant determines the strength of gravity everywhere matter exists. Planck's constant determines the behavior of quantum energy everywhere particles interact. These constants are universal. They are measured values, discovered through experiment, baked into the fabric of physics by whatever process produced the universe's laws. Combine these three constants in the specific way that produces a unit of length, and you get the Planck length. The combination is unique. There is only one way to multiply and divide these three constants to produce a quantity with the dimensions of length. The answer is fixed by the constants themselves. An alien civilization on a planet orbiting a distant star, using entirely different languages, entirely different numbering systems, and entirely different base units, would still discover the same three constants when they developed advanced physics. They would calculate the same combination, and they would arrive at the same physical length, expressed in whatever units their civilization had invented. The number would look different, but the physical distance it described would be identical to ours. This universality is remarkable. It means the Planck length is not a product of human culture. It is a feature of the universe that any sufficiently advanced intelligence would encounter and recognize. An inscription of the Planck length in a message to an alien civilization would be immediately meaningful to them if they had reached the level of physics required to decode it. It is one of the few pieces of information that transcends all cultural context. Wheeler saw this universality as evidence that the Planck length was pointing at something real, a feature of the universe's own structure, not an artifact of how humans chose to organize their measurements. Planck had said something similar when he first derived his natural units in 1899. He wrote that these units retained their natural significance for all times and all cultures, even extraterrestrial and superhuman ones. He was right about their universality. What he could not have fully appreciated was what they were pointing at. Every civilization that discovered these constants and combined them would also, eventually, discover the same wall, the same breakdown of geometry, the same minimum length enforced by the same collision of quantum mechanics and gravity. The wall is not a human construction. The universe built it into itself. And that raises the question that haunts modern physics more than any other. Does this wall mean the universe is discrete? Does it mean reality is pixelated? Does smooth, continuous space actually exist? Or is it an illusion produced by coarse instruments? Physics rests on two pillars. The first is general relativity, developed by Einstein and published in its complete form in 1915. It describes how gravity works at large scales. It explains the orbits of planets, the behavior of black holes, the expansion of the universe, the bending of light around massive objects, and the relationship between mass, energy, and the curvature of spacetime. Every prediction general relativity has made has been confirmed. Gravitational waves, predicted in 1916, were finally detected a century later, exactly as the equations described. The theory works with extraordinary precision across scales, ranging from a few miles to the entire observable universe. The second pillar is quantum mechanics. Developed through the early 20th century by a generation of physicists including Heisenberg, Niels Bohr, Erwin Schrödinger, and Paul Dirac, quantum mechanics describes how matter and energy behave at the smallest scales. It explains the structure of atoms, the behavior of electrons, the nature of light, and the interactions between subatomic particles. Quantum mechanics is the foundation of chemistry, semiconductor physics, laser technology, and much of modern electronics. Every quantitative prediction quantum mechanics has made, and it has made thousands, has matched experiment. Each theory is the most successful framework ever developed in its domain. Each has been tested more thoroughly than almost any other idea in the history of science. Each has never failed a direct experimental test. At the Planck scale, they collide head-on and destroy each other. General relativity treats spacetime as a smooth, continuous, precisely defined structure. It requires geometry to be well behaved everywhere. Its equations break down when spacetime curvature becomes infinite, which happens inside black holes and at the moment of the Big Bang. These breakdowns are called singularities, and they signal that the theory is being pushed past its limits. Quantum mechanics requires the uncertainty principle to apply everywhere. At the Planck scale, this means the geometry of spacetime fluctuates violently and unpredictably. Quantum mechanics cannot accommodate a fixed smooth background. It demands that every physical quantity, including spacetime geometry, be subject to quantum uncertainty. These demands are mutually exclusive. General relativity needs smooth geometry. Quantum mechanics destroys smooth geometry at the Planck scale. Apply both simultaneously, and the mathematics produces outputs that are physically meaningless, infinite energies, infinite densities, probabilities greater than 100%, spatial distances that become imaginary numbers. Physicists have known about this incompatibility for nearly a century. Unifying these two theories into a single consistent framework is the central unsolved problem of modern theoretical physics. The theory that would accomplish this is called quantum gravity. Building it has been the goal of some of the most brilliant minds of the last 100 years. So far, it does not exist. String theory is an attempt. Loop quantum gravity is an attempt. There are others: causal dynamical triangulations, causal set theory, asymptotic safety. Each represents a serious mathematical program developed by serious physicists. Each captures some features of what a quantum gravity theory needs. None of them has produced confirmed experimental predictions that distinguish it from the others. The universe keeps its deepest secret, but what that secret means for everything above it, from the smallest atom to the largest galaxy, is profound. A photograph looks smooth. Hold it at arm's length, and you see a continuous image, gradients flowing seamlessly from one colour to the next, no visible breaks or discontinuities. Zoom in far enough, however, and the smooth image reveals itself as a grid. Individual pixels appear, each a single block of uniform colour. The smooth gradients dissolve into staircases of discrete squares. Below the pixel level, there is no more image. The photograph has a resolution limit, and at that limit, the idea of a smooth continuous picture stops being true. If loop quantum gravity or similar frameworks are correct, reality works the same way. At everyday scales, space looks and behaves like a smooth continuous medium. Light travels through it in straight lines. Particles move along well-defined paths. Geometry works exactly as Euclid described it 2,000 years ago. The smooth picture of space matches every observation so well that questioning its smoothness seems unnecessary. But if space is made of discrete chunks at the Planck scale, then the smooth picture is an approximation. An image that only looks smooth because our instruments are nowhere near fine enough to see the pixels. Every measurement ever made by any human instrument has been the equivalent of viewing a photograph from across the room. The implications of a pixelated universe cascade in several directions at once. For one, it would mean that space cannot be divided infinitely. The infinite divisibility of space, the assumption that you can always find a smaller distance between 2 points, would be false. The universe would have a coarseness built into its foundation, a resolution limit below which no location, no distance, no measurement has any meaning. For another, it would mean that continuity in physics is an illusion. Equations that treat space and time as continuous would be revealed as effective approximations, valid at accessible scales, but fundamentally wrong at the deepest level. Every integral in physics, every equation that sums over continuous ranges of values, would be a smooth approximation to something actually discrete. This possibility has been explored in information theory as well. Some physicists have proposed that the universe is, in some meaningful sense, computational, that the discrete Planck pixels of space-time process information in a way analogous to bits in a computer. John Wheeler himself expressed this idea near the end of his career with the phrase "it from bit," suggesting that physical reality emerges from information. These ideas sit at the boundary between established physics and serious speculation. They are taken seriously by some of the field's most respected thinkers and viewed skeptically by others. The experimental evidence to decide between them does not yet exist, but the core possibility that smooth continuous space is an illusion produced by operating far above the Planck scale remains entirely consistent with everything physics has measured, and if it is true, then every map ever drawn, every distance ever measured, every equation ever written, has been a blurry approximation of something granular and discrete underneath. The rulers humans use to measure the world would be, at their deepest level, touching something they were never designed to see, and any ruler built to actually reach that level would immediately face a problem that has nothing to do with accuracy. Consider what a ruler is. Physically, it is a rigid object with marks at defined intervals. Its usefulness depends on it holding its shape, remaining stable across the distance it is measuring, and not disturbing the thing being measured. A good ruler is stiff, precise, and passive. It sits alongside the thing being measured and does nothing except provide a reference. Now apply these requirements to a ruler designed to measure the Planck length. First, the ruler needs marks at Planck length intervals. The marks must be physically distinguishable from each other, meaning the material making up the ruler must have internal structure smaller than the Planck length, but the Planck length is the minimum structure in the universe. No material can have internal features smaller than it. The ruler cannot be marked at this precision using any physical material, because physical materials are made of particles, and particles are vastly larger than the Planck length. Second, assume we somehow overcome this and build a theoretical ruler. This ruler now must be rigid across a length that includes at least one Planck interval. Rigidity in materials comes from electromagnetic forces between atoms. The ruler holds its shape because the atoms in it resist being pushed apart or squeezed together. But at the Planck scale, the atoms making up the ruler are enormous compared to the length being measured. The ruler's own atomic structure is billions of times too coarse to register Planck scale marks. Third, and most destructively, the ruler must have enough energy density to define a stable physical structure at this scale. Any object with a well-defined position and structure at the Planck length must, by the uncertainty principle, carry enormous energy. An object carrying the energy necessary to be physically real at the Planck scale carries enough energy in a small enough volume to generate a gravitational field that collapses the object inward. The ruler crushes itself before it can be used. This is not a materials engineering problem. No better alloy, no stronger structure, no more exotic matter resolves it. The collapse follows from the fundamental relationship between energy, mass, and gravity. Pack enough energy into a small enough space, and that space becomes a black hole. The Planck length sits precisely at the threshold where this always happens. Any object stable enough to mark the Planck scale carries enough energy to collapse into a black hole. Any object light enough to avoid collapsing is too energetically uncertain to have a defined position at the Planck scale. The two requirements exclude each other completely. This is another version of the same wall appearing from a different direction. Every approach to the Planck scale whether through light beams, particle probes, or hypothetical rulers, produces the same result. The measuring tool destroys itself, creates a black hole, or loses all meaningful information before the measurement can complete. The universe has built multiple overlapping enforcement mechanisms into the same prohibition. It is not content with one reason. It provides several simultaneously, each independently sufficient to make the measurement impossible. The last time physics encountered a situation this thoroughly walled off, it was pointing at something new, something the existing framework could not describe. A threshold that marked the edge of one era of understanding and the beginning of the next. The Planck length may be pointing at the same thing. And the event that happened at this scale 13.8 billion years ago may hold the deepest clue. The universe began roughly 13.8 billion years ago in an event called the Big Bang. The name is misleading. It was not an explosion in the conventional sense. Space itself expanded from an extraordinarily hot, dense state into the vast, cold, sparse universe we observe today. The process continues. Every galaxy is moving away from every other galaxy as space itself stretches. Running the expansion backward produces a picture of the early universe that gets hotter, denser, and smaller the further back you go. Standard cosmology can describe conditions going back to roughly 1 second after the Big Bang with good confidence. High-energy physics can push that back to fractions of a second, describing temperatures and densities that no laboratory will ever recreate. At some point in this backward journey, the universe reaches a state so hot and dense that the Planck scale becomes relevant. This moment, called the Planck epoch, is when the universe was roughly 1 Planck length across. The Planck epoch lasted from the absolute beginning of time until roughly 10 million trillionths of a second after the Big Bang. That duration is so short that it has no intuitive analogue. During this window, the entire universe fit inside a volume the size of the Planck length. Every particle, every force, every piece of matter and energy that would eventually expand into the observable universe existed, compressed into a region where geometry breaks down, time loses its direction, and our current physics produces only infinities. This means the Big Bang itself is unreachable by current physics. The moment of greatest interest, the beginning from which everything followed, is sealed behind the same wall as the Planck length. Our equations reach that threshold and then fail. Running the backward journey past the Planck epoch returns nonsense. Infinite temperature, infinite density, infinite curvature. The singularity in the equations marks the edge of what physics can currently describe, not necessarily the edge of what actually happened. Whether the universe existed before the Planck epoch in some form, whether it bounced from a previous contracting phase, whether the Big Bang was the true beginning of time or an event within a larger structure, are all questions that cannot be answered without a working theory of quantum gravity. The Planck scale hides the answer to the most fundamental question cosmology asks. What emerged from the Planck epoch was a universe governed by forces and particles that had separated from a unified high-energy state. The smooth, cool, structured cosmos we inhabit is the end product of 13.8 billion years of evolution from that unknowable beginning. The Planck length is not just a limit on measurement. It is the horizon behind which the origin of everything is hidden. The wall we cannot see past is the wall that separates us from the moment all of this began. And sitting just behind that wall is a question that physicists have argued about for more than a century. A question about the deepest nature of space. A question with enormous consequences for everything built on top of it. The ancient Greek philosopher Zeno of Elea proposed a series of puzzles that have annoyed mathematicians and physicists for 2,500 years. His most famous one goes like this. An arrow in flight must first travel half the distance to its target. Before it reaches the target, it must first reach the halfway point. Before reaching that halfway point, it must first reach the halfway point of the halfway point. This process of halving continues forever. The arrow must pass through an infinite number of points before arriving. How can something pass through infinite points in finite time? And yet arrows fly. And yet they land. Zeno was not arguing that motion is impossible. He was exposing a tension in the idea that space is infinitely divisible. If you can always find a halfway point, then every journey involves infinitely many steps. Mathematics eventually developed tools to handle infinite sums that converge to finite values, which resolved the mathematical version of the paradox. But the physical version, whether space is truly continuous or whether it eventually becomes granular at some fundamental level, was never fully settled. It just moved from philosophy into physics. The debate has two sides with very different pictures of reality. On one side, continuous space. Space is a smooth, unbroken medium with no minimum size. Between any 2 points, no matter how close, another point always exists. Distances can be divided indefinitely without ever hitting a floor. This is the assumption built into virtually all of physics as currently written. Calculus, which forms the mathematical backbone of physics, requires continuity to function. The equations of general relativity require smooth spacetime. Quantum field theory, the framework that combines quantum mechanics with special relativity, is built on continuous fields spreading through continuous space. On the other side, discrete space. Space has a granular structure at the Planck scale. The Planck length is a genuine minimum. Below it, there are no more points, no more distances, no more spatial structure of any kind. Space is made of finite chunks, and the smooth appearance of space at accessible scales is what a chunky structure looks like from very far away. Both options have severe problems. Continuous space leads to the breakdown of physics at the Planck scale. The equations work beautifully above it and produce nonsense at it. If space is truly continuous, something must change dramatically at this scale, something not yet captured by any existing theory. Discrete space requires explaining where the chunks come from, why they have the size they do, how they connect, and how smooth spacetime emerges from them at large scales. None of these questions has a fully satisfying answer in any current theory. The Planck length sits at the centre of this debate because it is the scale at which the question must be answered. Above the Planck length, both continuous and discrete space produce identical observable predictions. Below it, they diverge completely. The answer matters enormously for physics, but the answer sits in exactly the region that is experimentally inaccessible. The question Zeno asked in ancient Greece, dressed in the language of quantum gravity, remains open today. If the Planck length is a genuine minimum, a true pixel of space with nothing smaller beneath it, the consequences for science stretch far beyond a single number in a textbook. Every equation in physics that uses calculus would require re-examination. Calculus assumes continuity, integration, the mathematical tool used to calculate everything from the trajectory of a cannonball to the energy emitted by a star, works by summing infinitely many infinitely small contributions. If space is discrete, this operation is an approximation. A very good one at everyday scales, but an approximation nonetheless. The true equations governing the universe at its deepest level would be discrete, summing over finite chunks rather than integrating over continuous ranges. the consequences for computing would be profound. A universe with a finite information density per unit volume has a maximum amount of information that can be stored in any region of space. Physicist Jacob Bekenstein showed that the maximum information content of any region is proportional to the area of its surrounding surface, measured in units of the Planck length squared. If you tried to store more information than this limit in a given volume, the region would collapse into a black hole. The universe has a hard drive with a finite capacity per unit volume, and the Planck length sets the size of the bits. For cosmology, a discrete minimum length would help tame the singularities that current equations produce inside black holes and at the Big Bang. Singularities arise in continuous mathematics when quantities are divided by zero or pushed to infinity. In a discrete framework, you cannot divide by zero because the smallest possible distance is the Planck length. Division stops there. The infinity is cut off. Some theories of loop quantum gravity show exactly this. When the evolution of the early universe is calculated using discrete equations, the Big Bang singularity is replaced by a bounce from a previous contracting phase. The universe did not begin at a point of infinite density. It reached a maximum density at the Planck scale and then rebounded. For fundamental physics, confirmation that space is discrete would be the most significant result since the discovery that energy comes in quanta in the early 20th century. It would signal the end of the smooth, continuous picture of reality that has dominated physics for 4 centuries and replace it with something granular and finite at the base. Every theory would need to be rebuilt from this new foundation, and for humanity's sense of its place in the universe, it would confirm that the smooth, seamless world of everyday experience is a high-level approximation of something radically different beneath. Every table, every rock, every breath of air is made of atoms, which are made of quarks, which exist far above a granular space-time that churns and fluctuates at a scale we will never directly perceive. The smoothness of the world is borrowed from the coarseness of our perception, and the truth at the bottom is something physics is still struggling to name. Physics has been hunting a single unified theory for over a century. The goal is a framework that handles both the very large and the very small within one consistent set of equations. General relativity owns the large. Quantum mechanics owns the small. At the scales where both are relevant simultaneously, which means the Planck scale, neither works alone, and combining them produces contradictions. The theory that resolves this contradiction is called quantum gravity, and finding it is the deepest open problem in all of science. The history of physics is a history of unification. James Clerk Maxwell unified electricity and magnetism into a single framework in the 1860s and discovered that light was an electromagnetic wave. Einstein unified space and time into spacetime and showed that mass and energy were interchangeable. In the 1970s, physicists unified 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, into a single theoretical framework called the Standard Model of Particle Physics. The Standard Model is extraordinarily successful. It predicted the existence of dozens of particles before they were detected and has been confirmed by thousands of experiments. Gravity refuses to join. Every attempt to include gravity in the Standard Model framework produces infinities that cannot be removed. The mathematical technique used to tame infinities in the other forces, called renormalization, fails for gravity. The infinities gravity produces are of a different kind, a more severe kind, and no procedure within the Standard Model framework cancels them out. Gravity keeps breaking the machine. String theory attacks this by replacing point particles with extended strings, which spreads the problematic infinities out over a length scale and allows them to cancel. Loop quantum gravity attacks it by quantizing spacetime directly, building gravity from a discrete structure rather than adding it to a continuous background. Other approaches propose that spacetime is emergent, not fundamental, arising from some deeper layer of reality not yet identified. All of these approaches are decades old. All have produced beautiful mathematics. None has generated a confirmed experimental prediction. The frustration is real and widely acknowledged in the physics community. Some theorists worry that the lack of experimental access to the Planck scale may mean quantum gravity will never be confirmed by direct test. The theory might be mathematically consistent and physically correct, and yet remain forever beyond the reach of experiment. Science would then face a new kind of problem, a theory that cannot be tested, about a domain that cannot be accessed, answering questions that cannot be resolved any other way. Others remain confident that indirect tests will eventually accumulate enough evidence to point to the correct answer. Gravitational wave astronomy, gamma-ray burst observations, and precision cosmological measurements each probe different aspects of space-time at different scales. The collective evidence may eventually build a picture coherent enough to distinguish between competing theories. The search continues, and what drives it is the certainty, shared by everyone in the field, that the current situation is unsustainable. Two perfect theories that are mutually incompatible cannot both be the final word. Something lies beneath them, something that the Planck length marks the entrance to. The door is sealed, but the search for a key continues. Science has always pushed boundaries. Galileo pointed a telescope at Jupiter and found moons orbiting it, shattering the belief that everything revolved around Earth. Physicists in the 20th century smashed atoms and found they were mostly empty space with a dense nucleus at the centre. Astronomers discovered that the universe was expanding, that galaxies were flying apart, that the cosmos had a beginning and would have an end. Every generation of scientists found that the universe extended further, contained more, and operated at scales beyond what previous generations had imagined reachable. The Planck length is where this pattern of expansion appears to stop. Every other limit science has encountered was either a practical limit, waiting for better technology, or a conceptual limit, waiting for a better framework. The Earth was not the centre of the universe, but the physics needed to demonstrate this existed and needed to be discovered. Atoms seemed impossibly small until instruments were built to see them. The cosmic microwave background, the afterglow of the Big Bang, seemed impossibly faint until radio astronomy developed the sensitivity to detect it. Each barrier fell because the barrier was, in the end, about access, not about the fundamental structure of reality. The Planck length is enforced by the fundamental structure of reality. It is not a practical limit awaiting better instruments. Every conceivable improvement in instruments runs into the same wall, because the wall is built from the same laws that govern how instruments work. The most powerful probe imaginable, using the most advanced physics conceivable, following any physically allowed strategy for measurement, produces a black hole before it reaches the Planck scale. The wall does not weaken as technology improves. It holds because the laws that enforce it are the laws that make technology possible in the first place. This places the Planck length in a unique category. It is the scale at which physics acknowledges the limits of its own reach, the scale at which the questions stop having experimentally accessible answers, the scale at which the two greatest achievements of human scientific thought collapse into each other and produce contradictions instead of predictions. Some physicists find this deeply unsatisfying. Science is built on the premise that any question about the physical world can in principle be answered by observation. A question permanently shielded from observation violates the spirit of the scientific method. if quantum gravity produces predictions that can never be tested. It raises uncomfortable questions about what it means to call something a scientific theory. Others find it clarifying. The Planck length gives science a precise location of its own boundary. It does not say the universe has nothing below this scale. It says that whatever is below this scale is inaccessible to any method of observation that respects the laws of physics. The universe has a knowable region and apparently an unknowable one. And the dividing line between them has a precise address. That address is the Planck length. And the question it leaves behind may be the most honest question physics has ever asked. Humans have always been most afraid of what they cannot see. The darkness before a candle is lit, the deep water where the light runs out, the silence after a sound that cannot be identified. The imagination fills these spaces with something, because leaving them empty feels worse. We build stories about what lives in the dark. We name the thing we cannot see. We give shape to the shapeless because the alternative, accepting that some things have no accessible shape at all, is deeply uncomfortable. The Planck length is physics acknowledging that some spaces cannot be lit. For centuries, science made a promise, implicit but powerful. The universe is knowable. The tools may not exist yet, the mathematics may be undiscovered, the experiments may be decades away, but the answers are out there, and science can reach them. The promise drove enormous progress. It justified enormous effort. And it was, for a long time, kept at the Planck scale. The promise encounters its hardest test. The true structure of space-time at this scale may be permanently inaccessible. The nature of quantum foam, the correct description of the Big Bang's first moment, the resolution of the conflict between general relativity and quantum mechanics, all of these answers live behind a wall that physics itself enforces. The laws of nature prohibit the measurement. The barrier is not waiting for a key. The barrier may be the lock and the key at once, and yet this is not a defeat. The Planck length, precisely because it marks the edge of knowable reality, tells us something extraordinary about the universe we inhabit. A universe with a minimum length is a finite universe in a deep sense. A universe where geometry breaks down at the smallest scale is a universe with a structure to its foundation, a graininess, a texture. A universe where two perfect theories collide and destroy each other at one specific scale is a universe that is pointing, urgently and clearly, at something beyond those theories. Something not yet discovered, something that may be the deepest truth about the fabric of existence. Every great discovery in physics began as a breakdown. Newton's mechanics broke down at high speeds, and special relativity emerged. Special relativity broke down in strong gravitational fields, and general relativity emerged. Classical physics broke down at atomic scales, and quantum mechanics emerged. Each time the breakdown seemed like a failure. Each time it was a door. The Planck length is the biggest breakdown yet, the most complete, the most fundamental, the most stubbornly unresolved. It is where both of the greatest theories ever constructed simultaneously reach their limit and point, together, at something beyond themselves. Whatever lives past that boundary may require a revolution in understanding that makes quantum mechanics and general relativity look like footnotes. The universe built a wall. And everything humans know about walls suggests that walls exist because something is on the other side. The darkness at the Planck scale is the most honest darkness science has ever named, and in naming it precisely, physics has done something remarkable. It has drawn the exact shape of everything we do not know. That shape is the size of one Planck length. and it contains everything.